The task that I was given to talk about was this, going from empirical to mechanistic to AI models, making livestock production more efficient. So I decided to actually take this through the lens of a research project that my group has been working on for the last, I'll say, 5 or 6 years. And I'm going to take you through an odyssey through our adventure using empirical models and some machine learning, and now looking back to mechanistic modeling on that topic. This slide feels a little bit like preaching to the choir here, but we're going to do it anyway, right? I think it's really exciting, actually, that we're witnessing in real time, this agriculture 4.0 revolution, and this fusion of animal production systems with emerging digital technology, right? And I start to think, that some of the barriers of the past, looking at things like data capture capabilities, like what we're actually able to measure, and not only that, like the efficient data capture or the automated capture of those pieces of information is really revolutionary in terms of what we're able to model. And then also now that we have these appropriate, analytical approaches to analyze that data. And it brings up so many opportunities, I think, for the future in terms of system optimization and decision support. And probably we will see full automation of certain aspects of that animal production system as well. Okay, so what do I want to talk about today? I want to talk to you a little bit about feed manufacturing and our adventure through a variety of modeling approaches to this task. And this project actually has kind of a fun origin. So I spent a couple of years working in industry. I was a poultry nutrition modeler for Trout Nutrition. And during that time, I was running an experiment. I was running a 2x2 factorial experiment, which was looking at the effect of ingredient selection and also manufacturing conditions on poultry performance. Well, actually what happened is also, the important point here is because you're working in industry, we were actually manufacturing these diets in a commercial mill. And if you've ever tried to manufacture a very precise experimental diet in a commercial mill, you will soon understand that, we formulate to the third decimal point, and then it's like a turn of the auger difference, in terms of composition. So there's big differences in accuracy. I have to say that 2 of my diets were completely compounded with poor pellet quality. And that impacted animal performance. So I learned a couple things through this exercise. One, I learned how to say sorry to my boss for kind of botching the experiment. I also learned that pellet quality had a big impact on the animal performance. But as a modeler, I sat and I looked at the mill, and I was like, this is a big data generator. There is so much information coming in and out of this mill, and it all impacts pellet quality. But the really interesting thing was, on a 7-day rotational cycle, all of this information was being deleted and essentially overwritten. So none of it was being saved, right? So for me, as a modeler, this brought kind of an idea from a problem, so I thought I liked that point from the previous speaker, that this project originated from a problem, and I thought, we can tackle this. So for those of you who might not be familiar with, with feed manufacturing and that process, we essentially take, where we make this agglomerated feed by extruding individual ingredients or mixtures and compacting and forcing them through a die opening by some mechanical process. And the benefits of pelleting feed are numerous, right? So we know that it can improve animal performance. It can help improve things like digestibility, reduce feed sorting or wastage, and it can also improve feed conversion. And probably from a management perspective, it also improves things like flowability, and also it increases the density of the feed, so it makes handling it much easier. So pellet quality, right? So the pellet quality is really the ability of that pelleted feed to withstand the handling and abrasion that happens after it's manufactured in the mill and it gets shipped through trucking, and then it probably gets blown through piping in an auger, for example. So its ability to maintain its structural integrity. And we use something called pellet durability index as a metric of this pellet quality, right? So pellet durability index, or PDI, is a widely used measure of pellet quality. We measure it in the mill, right? So we make the feed, we measure the PDI, and then we ship it. And this is a metric of what might happen to that pellet quality by the time it reaches the animal. So the PDI measure, there's a few different ways to measure this. Either a tumbling method, which is the ASAE method, or the Holman tester, which is shown here. And essentially what we do is we expose the pellets to some kind of tumbling or blowing insult, and then we look after a specified period of time the amount of pellets that are left intact, right? So this is kind of a percent out of 100 of what pellets are left intact after this kind of treatment. And this is a metric of what we might expect in front of the animal. So we know that pellet quality is impacted by a host of things, right? Both the manufacturing conditions, things like conditioning temperature, also the nutrient content of the pellet, things like the fat content or the protein and starch content. We know the nutrients impact it, and anecdotally, you know, this is fun because as we got into this project and talking to mill operators, they'll always be like, you know, mill operator. Like some people just know how to pellet certain products, and for example, if they have something that's really difficult to pellet, they're going to give it to Jay because Jay's really good at pelleting that run. And it's some combination of experience and listening to the sounds, for example, that the mill is making, that they know how to pellet that, right? So anecdotally, you get some fun things like this when you talk to people. So what's been done in this area? Well, there's a lot of studies in the literature that have looked at how different ingredients, nutrients, manufacturing conditions impact pellet quality. So there is a suite of published papers out there on this. When we started this, we could only find one, let's say in the published literature, because that doesn't mean that some feed company hasn't tackled it. But we'll say that we found one paper at the bottom there that looked at some empirical statistical modeling approaches to predict pellet quality using a semi-commercial facility. So this really led us to ask the research question then, can we predict PDI in the commercial feed mill? Right? So can we predict this outcome given all the things that are changing in the mill? And the downstream application is really then, can we use the model to optimize pellet quality and potentially other aspects of feed manufacturing? So this eventually becomes a story about machine learning, but actually where we started first is we wanted to say, well, actually, there are a lot of papers in the literature on pellet quality. Can we use a meta-analysis approach to predict PDI? And this is what I'm going to show to you first, but it's actually not published yet. It's probably going to be one of the last papers that we publish, but I'm going to show it to you chronologically this way. So what we did is we performed a systematic literature review with specified inclusion-exclusion criteria to identify papers in the literature that looked at a combination of manufacturing, nutrient composition, and ingredient selection impacts on pellet quality. We identified through this 280 treatment means from 29 studies. They had to have the PDI measured via this ASAE methodology, which was at the time the most prevalent method used in literature. And we ended up with about 16 variables or features that we could use for model building across ingredients, manufacturing parameters, and nutrient composition of those pellets. Now, this is what happens when you give a meta-analysis task to a data science student, which is that they make a data processing pipeline out of it, which is great. But essentially, my PhD student, now postdoc, took this task on, and from those kind of 280 treatment means, looked at essentially some initial variable selection. So, for example, some features or things that were measured in different studies were not reported consistently across studies. So for example, if features were reported in less than 6 studies, we removed those from consideration, right? So things like, I think it says like wheat and fiber percent, they weren't reported regularly across these studies, so we removed them from consideration. We also did some screening based on which features were varied within studies. So some features, like the die hole diameter, didn't vary at all within study. And so features with a high consistency rate within study, we also looked at removing some of those from consideration. For model development, we did the standard mixed model development, treating study as a random effect. And then everything was kind of evaluated in sequence things. We did outlier evaluation. We analyzed the residuals. We looked at for multicollinearity between the features and also considered the significance of those features in the end. So we also performed in this. It's very difficult to do this with a limited data set, but we've performed a threefold cross-validation. So the results I'll show you are from that independent evaluation piece of it. And we used a variety of measures or metrics to evaluate model performance, like mean square prediction error, CCC, and some visual plot evaluation. Okay, so these were kind of the best models that came out of it. I circled one. I'm not sure how easy you can see it. Essentially, but one of the best performing models was based on the lipid and the protein content of the pellet. So the lipid having a negative impact on pellet quality, which is known. So lipid and fat tends to have a lubricating effect as a mash goes through the die. So this made sense. And also the protein, the positive protein impact is also reflected in our knowledge on the topic. At the bottom, let's see if this is, yeah, this guy down here, this is our model evaluation in that threefold cross validation. So our best CCC was about 0.29 on that independent evaluation, okay? So we'll call that, I don't know if we want to call it poor, but it's definitely modest at best, okay? So what did we develop, or what did we learn through this, right? So we built some simple models to predict PDI. The CCCs are not great, right? But we also have to think, I think as we think about moving this field forward, we also have to realize that this hyper state of automation is not going to be consistent across the board in terms of our feed mills and our farms. And so there's still a lot of value in developing simple models to apply. For example, many of the feed mills that we've talked to have zero state of automation at the moment, right? And if you can have a simple formula that they can input into brill or breast mix to give them an idea of what that pellet quality is going to be, that still has value, right? Not all mills are going to be hyper automated. However, I decided to push my limit here a little bit, and I was like, okay, well, how do they perform? How do these equations that we just built perform in a commercial mill? Because you'll see, I'm going to talk about some of our commercial mill data next, and it's not pretty. So this is what happened. This is our predicted versus observed. So this is one of our commercial mill data sets, and I think our CCC was like minus 0.03. It's not good. There's no relationship. There's probably a few reasons for this, which is important. One is that all of our data sets from the commercial literature use this ASAE method, which essentially, I think, takes the pellets and it tumbles them for 10 minutes, I believe. The industry has moved towards a Holman tester, and all of our commercial mills that we've worked with are using a Holman tester, which essentially blows the pellets for 30 seconds or a minute. So I think that much of this bias is actually because the industry has moved to a different method compared to what the published literature is in, which I think is another important take-home point when we develop models on research data from the scientific literature, that they don't always match with what's happening live in the industry. So that's one of the reasons why I think that this is poor. The other one is that we know that more than just lipid and protein impacts pellet quality, right? This doesn't take into account any of the manufacturing conditions at all, okay? So this was a grounding exercise, really. So it left us with the question, though, can we do better than this, right? So this is, what I'll show you next is the results from a project that we did from about 2020 to 2023. So this was funded by the OMAFA, which is the Ontario Ministry of Agriculture and Food. And Trow Nutrition was our major research partner for this, and they provided all the mill data for this exercise. So essentially what we wanted to do is say, okay, can we do better? Can we predict this pellet quality in a commercial feed mill using machine learning? And everything that I'm gonna show you today, actually, I'll just say is the work of my, this was my PhD student's PhD project, and he's now my postdoc continuing to work on some of this. So I definitely want to acknowledge that I'm going to use his name in vain a lot today. This is all of his work. And I also just want to acknowledge here Dan Tulpan, who I think you've heard from in previous years in this symposium, who's phenomenal, and he co-supervised GHOW with myself. So, right, why might machine learning be a good tool to apply to the commercial feed mill? Well, as I said before, the feed mills are generating a ton of data, right? They are naturally big data generators. And we definitely are getting, these V's that we usually describe big data, the volume, right? We're producing tons of data in real time. Variety of data, right? Velocity, real time, and we'd like to analyze it in real time. And veracity, which is really about data quality. And GHOW can definitely attest to the need to clean and process this data before model building could commence. So the data that we used for our kind of first trial on this was hand collected, we'll come back to that, for about 7 months by the mill operators, which means that they're looking at the computer and then they're writing down the conditioning temperature, et cetera, right? This data included, we ended up getting about 1,400 observations, where each observation is essentially a run of a formulation through the pelleting mill. Okay? We had 17 variables, which were essentially split across the ingredients that were used and the manufacturing conditions. Okay? We took this data and split it into 2 subsets, right? So we took 80% and we kept it for model development. On that, we did a 5-fold cross-validation, and then we withheld 20% of it, and we used that 20% for independent model evaluation. Okay, so all the model evaluation results I'll show you are on that 20% that the model never saw. We also evaluated 12 different machine learning algorithms and applied them and compared them to see which would be best to attack this problem. These are the features that we had available to us for this, this exercise. So we had a number of ingredients, the main ingredients, not all the small ones, but the main ingredients. We had information like feeder speed and conditioning temperature, et cetera. And I always say quite cleverly in hindsight, my PhD student also took information from a regional weather station to essentially get the temperature and humidity at the time that the pelleting was happening. So these are the learning curves from these models, right? So there's 12 for the 12 different models. And essentially what you're looking at is on the y-axis being the MAE, the mean absolute error, right? So smaller, better, bigger, worse. Okay, and on the x-axis, this is the size of the training set going from 0 to 80%, okay? The red line is the training curve, okay, and the green line is the testing curve. So what we would like to see in this diagram is a few things. We would like to see that that green curve and the red curve essentially reach a plateau together, right? If the green curve and the red curve are far apart from each other, like this one in the upper right, which was the random forest, essentially it means that the model did really great on the training data. Right? But when we gave it the testing data, it performed much worse, right? The MAE was much higher. And this probably means that the model overfit the data, right? It was learning the noise, and then when we gave it a new challenge, it was like, can't do it, right? So that's one thing. We also want to see that they're kind of reaching a plateau, which means essentially, which can indicate that we've given the model enough data that it's learned adequately from it, right? But if that line is still changing, it can mean that the model is still learning and it could benefit from more information. So these are a couple of things we're looking for here. These are the permutation feature importance graphs for all of these models. And essentially, down the y-axis is the list of all the features that we considered in the model, okay? And essentially, the bigger the red bar, the more important that feature was to that model prediction, okay? So not all the models perform the same way, which can be expected. They're different, they're picking up on different things, but there are some common patterns. And what we really found interesting from this first exercise was that that outdoor environmental temperature came up really important, which was interesting. I was skeptical about it, but we were really interested in this. It could be that there was a direct impact, right? So the temperature of the air that we're pulling into the mill and using for cooling, right? That could have an impact, or the temperature of the ingredients when we're pulling them in, right? Or it could be an indirect effect. It could be that there's some seasonality, for example, the nutrient content of those ingredients that we had that was coming in there that it was picking up, but we weren't really sure at this time, but it was interesting. The other really interesting thing that it's probably too small for you, but I'm going to tell you, the other interesting thing you can see from this graph is that fat did not come up as important. Now this boggled us for a few minutes, and then we realized why. We know that fat impacts pellet quality, right? It has this lubrication effect, but it didn't come up as important in these feature importance graphs. The reason why is we're working in a commercial mill, and they already have controls in place to limit the amount of fat that's going into the mixer. So these models have never seen a high fat value. And so these models say it's not important. But the reality is it just hasn't seen it, right? So I think that's an important reflection as we build these models, that they're still very database dependent, right? And we need to show them the variability for them to learn it, right? So we interpret this with that kind of knowledge, right? These were the predicted versus observed plots. So I think we, at this point, eliminated 4 for a variety of overfitting, underfitting reasons. And I think this one down here, which was the SVR, was the best performing in terms of the CCC, so closer to 1 being better, and a variety of other evaluation metrics that we used. So, and maybe just a comment on this, and I'll come back to it later, that to me this is still quite a modest CCC in terms of performance, right? I feel like this is an honest CCC. This is not an overfitting model. I feel like this is a fairly honest evaluation, but we will talk a little bit more about that later. So we published this in 2022 in Animal Feed Science and Technology, and my PhD student at the time, my postdoc now, developed a user interface for this model. So the web link is there at the bottom if you wanted to play with it. Some of the interesting things here, we put in, you remember back to the beginning, I was like, yeah, the operator, when you talk to the mills, they're like, put operator into the model. So we tried. And so you can see this little toggle bar here. I'm not sure if that works, but this is the operator initials. To destroy the punchline, once you take into account, many of the other manufacturing parameters, this operator had a very small impact, but working with Dan Tulpen, who's got a great sense of humor, you would always say that this can't be used for hiring or firing. The other thing that's, I think, important to know is this was a fun pilot exercise, right? But if we look at the ability of this model to be used long-term, right? Well, what if JH leaves, right? And then we get a new operator called MD or something like that, right? So this is kind of like putting cow ID into your model. It probably makes your model work better, but it's gonna limit the applicability as soon as that cow leaves and you get a new cow, right? So this was fun to explore initially, but you'll see in subsequent models we took that out. What did we learn? Well, after about 7 months, the mill came to us and they were like, hey, they're like, we can't hand collect data anymore. It's just like, it's too much labor on the mill workers. They're like, but we see value in the project, so we're gonna modify our mill software. So NG is their mill software, and they spent a good 6 months and some money to essentially modify that mill software so that it would automatically capture all of that data, which was just being overwritten at the time, and download it into a big repository for us. So this was really great. So we've subsequently been capturing data from that automated system ever since. But the next study I'll show you essentially was taking a year worth of that automated capture data, which expanded both the number of observations, so the number of mill runs, and the number of variables or features that we could look at. So this third study essentially included around 2,700 observations or runs of the pellet mill and 76 variables. So we expanded, we went from our 16, 17 up to 76, and this is essentially an expanded list of the manufacturing and the nutrition and the ingredients, as well as expanding some of the, I'll show you in the next slide, some of the environmental information that we were collecting. Similar to the previous study, right, we took this data and split into 2 subsets, right? We took 80% for construction, we tried a 10-fold cross-validation here, and 20% was withheld for model evaluation. And Jiha wanted to try experimenting with some different approaches here. So he developed some statistical models to see what we could build. And we expanded, or we re-performed the exercise with the machine learning models as well. So I think I kind of covered this, right? So we now had this expanded list of features collected automatically by NG. The environmental factors, so we were really interested in this environmental impact from the first study. So we bought a whole bunch of temperature and humidity probes and placed them outside the mill and also throughout the mill to see if we could understand better what exactly was happening with that. So this is an example. This is a schematic of the feed mill, and the stars are essentially where we put the temperature and humidity probes. And there's always 2 at a time because we put 2 of them right beside each other in case one of them died, or to essentially check the values that each were giving us. So we put probes outside the mill. We put them at the air inlet and the air outlet locations through the mill. We put them at the bottom and the top of the mill, especially in the wintertime. There can be quite a temperature differential through the height of the mill. So we did this. Okay, so statistical models first, right? So Jihao played with a few methodologies. Just a linear mixed model analysis. He also played with some PCR and PLS methods. These were the features that came up as most important and essentially were included in the statistical model developed. I can just say, to save time, following the same kind of data pipeline and evaluation method we used in the meta-analysis earlier. Some of the other interesting things we did this time around was we created a few new features. And one of them was really interesting, called cumulative production. And essentially, frequently, or on a regular basis, the mill will change out the die, right, because of wear and tear. And so this is the cumulative production since the new die was changed, right? So this gives us an idea of that kind of wear that's happening over time to the die. Okay. These were the important features. The independent evaluation, we got to a CCC of about 0.55, right? So this is an independent evaluation of that. It's not quite as good as our last round of machine learning models, also not the same data set either, but it's not quite as bad as our meta-analysis models. So this was just published, this statistical modeling piece was just published in the Journal of Animal Science in 2025. So you can go find more information on that there if you want to. For the machine learning models, we went through the same exercise again, the same pipeline, evaluating multiple machine learning models, looking at overfitting, looking at the feature importance, et cetera. Kind of nicely, the same model, the SVR, was deemed the best performing model for this sort of data again. But perhaps to Jihao's disappointment, we increased the amount of features that we had from like 17 to 75, and then we actually also did some feature engineering in that, where we looked at the product of a couple of features, and we looked at the delta, the difference, for example, for the temperatures. And perhaps we were expecting a much better CCC here, but we ended up with a CCC of 0.61, which is very similar to the 0.64 from the previous machine learning exercise, but maybe a little bit lower even. And we'll talk about that, kind of come back to that at the end. These were some of the features that came up as important. So we definitely did see this ET as the environmental temperature. So this environmental piece does appear again. And then we've got a combination of those ingredients, the nutrients, and the manufacturing conditions coming up as important. So take-home message, right? So we've built a few things. We've done the meta-analysis. We've done some other statistical modeling approaches on the commercial data. And we've taken at least 2 swipes at the machine learning models on the commercial data. Not all of them give the same driving variables, but there is commonality amongst all of them, right? So we definitely see those fat, protein, starch content, the cumulative production, those kind of things, feeder speed, et cetera, right? But it really left us thinking, okay, so we've got a CCC of about 0.6 something, right? But what are we missing? Are we missing something? And the answer is probably yes. So the other piece that we know is really important for pellet quality, but that commercial mills do not routinely measure, is the particle size of the ingredients going into the mixer. We know that this impacts pellet quality. It's not something that the mills measure, right? So definitely there's that. The other thing too is, we take like a 500-gram sample out of a 30-ton run of feed, right? The other question was really, okay, so how reproducible is that sample? If we take that sample back to back to back, do we get the same results? Or if we take it 20 minutes apart, do we get the same result, right? Because this is a very small sample of a very large batch of feed. And I won't report on that in this presentation, but essentially we ran an experiment last summer across our mills to look at exactly this. And I think the punchline for that is the back-to-back-to-back samples are not significantly different, but if you measure 20 minutes apart, there are differences, right? So it depends where in that run you are taking your PDI sample as to what actual number that you're gonna get there. In general, the mills all will take that sample once the mill's at steady state, so there's an amp up period, right? But there's still a lot of fluctuation in ingredient chemical composition and the conditions of the mill over time, right? So that first project wrapped up, and it kind of left us being like, okay, so what next? So we put in a second project, and this one is just gearing up to finish later this year. It'll probably finish in winter of 2026. And the other real big question that we had out of this was, okay, so we built some machine learning models for one mill, right? Well, what happens, does that model work anywhere else other than that one mill? Right? We know that these kind of machine learning models can be very database dependent. So essentially what we've done is we've expanded this project. So we now have, or we have had, 4 different feed companies, and we have 8 mills in the project. So they're all within Ontario. So those 8 mills have been collecting data for us for the last year. And essentially we wanted to say, okay, can we build machine learning models for each of them individually? But then actually, can we build a generalized model that will work across them? Okay. I don't know yet if it's going to work, but we'll find out. Our hypothesis really in doing that was, we saw in the one mill the problem with the fat, right? That it was like the model said fat's not important, but we know fat, we know mechanistically, we know, physiologically, I always want to say physiologically because I'm an animal scientist. This is, this is not biological really, but we know that things like fat impact pellet quality. So our kind of hypothesis was, if we can manage to generalize this model and build it across different mills, that model will be exposed to more variable inputs. And perhaps, as a result, that model will better be able to answer what-if scenario questions like, what if we increase the fat content, right? So that was our hypothesis, that we would get more variable data and perhaps a more robust model. I don't have the answer to that one yet. You have to wait till next year. And then we also wanted to be able to kind of flip this around and say, can we turn it into an optimization algorithm? So can we actually say, we want this pellet quality, this is the formulation, what should we do different? Here's the levers that we can actually change. What should we do in order to get this PDI that we actually want? So I don't have the generalized model results. Jihao's still busy working on this. It causes him lots of stress. But what I do have is the results from one of our additional mills. So this is MFS, this is Molesworth Farm Supply. And we actually had 2 years worth of data collected from them. And with time on a project, you get new ideas, right? So there's a few new things that we wanted to try for Molesworth. And one was that they wanted to predict not only pellet quality, but also duration, right? So in the mill, the amount of time that it's going to take to run a batch of feed is an important kind of management, time management piece, right? They want to know, can we get this done in this time frame? And if they need to speed up the production of a batch of feed, we know it's going to have negative impacts on pellet quality. So it makes sense to build a model that can predict pellet quality as well as duration at the same time. So we had around 5,700 observations from Molesworth. We had a variety of features on manufacturing and the ingredient selection. We put the same temperature probes there as well, and the nutrient composition of the diet. So this is a little bit of what we did. We built some machine learning models using the same pipelines that we've set up for the other model building. We, again, used 80% of the data for model building with a 5-fold cross-validation, and 20% was withheld for evaluation. The other thing that Molesworth wanted us to do is they were like, okay, great. So, the last model that you built has like 115 inputs, right, with all the feature engineering as well. And they were like, that's not practical from an applied perspective. They're like, the automation is not to the point where all those inputs are coming into the model and then you just have to press run. They're like, we have to put all of those inputs into the model. And they're like, nobody's gonna do that. So they were like, can we do some feature selection based on all these information that we have to essentially identify a subset of important features and rebuild the model on that, because from an applied perspective, this is much more useful, right? So this is what we did. We built the models. We essentially looked at the feature importance, and I'll show you the permutation feature stuff, but actually Jihao's also been working on a unique method for identifying feature importance, which hopefully he'll publish later this year. But it's quite inspired actually by sensitivity analysis that we see a lot on the mechanistic modeling side. So this is kind of cool. This is coming, but I won't talk about that today. But essentially, we identified which features are important to the model, and then redeveloped the machine learning models on that more limited data set. These were some of the results from the full model for PDI. We got to a CCC of about 0.73, okay? So we did a little bit better here, and I've got some ideas why. We actually had less features. There was only 41 features here. But I actually think it's because we had more data. We had 5,700, or I think it was 5,700 runs instead of about half of that, and I think going through that annual cycle more than once had a positive impact on the model fitting here. And we actually looked at some B-swarm plots of the Sharp values, which is a different way to express feature importance, which gives us some directionality. So the permutation feature importance tells us it's important, but doesn't tell us the direction of impact. These plots can actually tell us that, for example, I'll pick a random one. Essentially, if it goes to red, it means it's increasing, and if it goes to blue, it means it's decreasing, right? So this gives us a little bit more insight into the direction of impact. We always want to know, kind of with these machine learning models, what's happening underneath the hood, right? So this gives us a little bit of a better idea of direction of impact. This was the duration model results. So perhaps not surprisingly, this CCC is like 0.97, which is quite high. But that's because we included in this the pellet weight. So this is like the total run size, how many pellets, how much weight of pellets do we want to manufacture? And not surprisingly, that's really related to duration, right? So that's the big driver, but then things like feeder speed, which is a lever that we can toggle and change, right? So that's something that the mill operators might do, is increase the rate at which we're producing pellets. And then we can predict from this like how long something would take, or how much we can decrease the speed by. So this is just a snapshot of the interface that Jihao developed for this model. So essentially, we have a more limited group of features, and we can predict pellet quality and duration at the same time. So this is how far we've gotten, right? We still have more to do, but essentially we've evaluated a number of statistical methods for predicting pellet quality, and then machine learning methods. We've started to do it across mills, right? So, but we've got 6 more mills to add kind of into this exercise. But we still kind of get to this CCC, we got to kind of 0.6 something, 0.7 something, right? Which I think are okay, but I think, are limited. So yeah, can we do any better? And this is the mechanistic piece. So by history, I'm actually more of a mechanistic modeler than a machine learning modeler. But there's some very cool work happening in Wageningen, actually. The work, Walter Gerrits has a student that's looking at the prediction of particle size reduction using a hammer mill. And I was like, well, this is really interesting, because this is information that we don't have at the mill. So they're looking at predicting things like the outflow of the particle size distribution. They've got a variety of driving variables based on things like the inlet mass feeder rate, the rotational speed of the hammer mill, residence time, et cetera. They've tested this on a variety of feedstuffs, and then the kind of mechanistic piece is really looking at like breakage kernel, the breakage rate, the screen selection function, and some of their early results. So this is just from an abstract that's published this year. They essentially looking at sensitivity that things like meal residence time explain the majority of the outcome variation. Great, well actually this is really interesting results, and we're looking at, there's some early conversations here to be like, hey, actually there could be some really useful partnership between what we're doing and this kind of mechanistic understanding that you guys are doing. Other work going on at Wageningen right now in this overall kind of related project. This group is looking at answering this question: under which processing conditions do loose pellet ingredients bond into rigid, durable pellets? Right? That's something we want to know too. So they've conducted a number of pilot experiments, and they've come up with this idea of a stickiness temperature, which is the temperature at which essentially there's enough moisture, heat, and friction that it enables bond formation within the pellet. And so they're modeling this kind of across the conditioner and then across the pellet die. And the cool part here is really this T-star, this stickiness temperature, is definitely the point when things start to pellet, but it's not a fixed universal value, right? It's very dependent on the mix that's going into the mill. And then coming from the machine learning background, or like perspective on this project, I think like, hey, that's maybe something actually that we could help with, is quantifying that aspect of the mix that could be used kind of to help this mechanistic piece. So, like I think one of my kind of passion areas, or I guess, or interest areas, is really bridging this gap and looking at how can all of these approaches really help each other. So, looking at this kind of research, I look and I think like, hey, maybe we should develop some new features for our machine learning models, looking at things like the delta temperature across the conditioner or the delta of the temperature across the die. These are not features that we have in our model, but the mechanistic understanding tells us that it is important, right? Maybe machine learning models can help to better define this T-star per mash, right? And maybe some of this mechanistic prediction of particle size can be useful to us in our exercise in machine learning as well. So what next? Really, this idea of this generalized model is something that we're working on over the next 6 months. And I'm really curious, kind of our next research proposals will probably be in the second and third point here. Which is looking at how can we actually collaborate with the mechanistic modelers on pellet quality to actually try to improve our predictions. And this other piece, the other thing that we're going to bring into this is actually an LCA analysis to be like, okay, great. Okay, so we can predict pellet quality, and does it matter, right? What's the energetic cost to the mill? And then what's the downstream impact on animal performance? So really, like, does it matter, and who's kind of paying the bill actually between those two pieces? I think from the commercial perspective, the real benefit to the mills that have been involved in this project is that they have now established these data pipelines, this automation step, which I think for all of those mills took at least a year. Like from our initial conversations to getting data flowing, it's at least a year. So this is an exercise that I think, we talk a lot about automation, but there has to be kind of a carrot at the end of the stick as like, why should we invest that time to do this? So I think projects like this show them that, we could actually do something with this data. And I promise I'm done. I think the challenges, I think the first one we already talked about, which is that we need to establish these pipelines. The second one, which I've been reflecting on a lot in the last 6 months, is that or the second and the third. So the second one, some important information isn't routinely collected in a commercial setting, right? So maybe our models will only ever get so good unless we have those missing pieces, which is something we can work on. And the last one is the one I've really been thinking of, which is that not all data is useful. We can collect everything, right? But maybe we can predict pellet quality from the top 30 instead of 150, right? But we actually won't know unless we look, right? So we have to set up these exercises to look at what's important. I just want to really quickly thank Jihao, who's my former PhD and now postdoc, who's doing all of this work, and Dan Tolpan, who's an extraordinary collaborator. And Thanks to Trow, Molesworth, Masterfeed, and Jones Mill for collaborating with us on this. It's actually also no small feat to have 4 competitors collaborating on a project together, but they see the value, which is why we're able to accomplish this. And feel free to reach out to me if you have questions about this project, but I'm also happy to take your questions when we have the roundtable. And that's it. Thanks, guys.